Look at the example here. We have a manufacturer making X items per day. The cost function, this is total costs. This question was a little ambiguous, so I added some notes here. The total costs is given by C of X equals 720 plus 4X plus 0.02X squared dollars. And the price function is P of X equals 15 minus 0.002X dollars per item. Now what makes this a little bit tricky is that the costs are total costs. This is the price per item. Okay? So it says find the production level that will maximize profits. Okay? Now if you think about the concept of profit, we're wanting to maximize profit. Now, since P is already taken, we'll use a capital F here. All right. How do you find profit? What's our
cost? No, what you sell minus cost.
It's revenue minus cost.
Okay, yeah, what you sell or revenue minus your costs. Okay. So we have revenue. We'll call that R of X minus your costs. All right, now, this is where this problem can be a little confusing. And actually, 7th period, we overlooked this, and that led us down a rabbit hole that we never, I didn't figure out until we were done. This is a dollars per item, so our total revenue, if we were to sell everything, is going to equal the number of items times the price per item, 15 minus 0.002x. Okay?
Okay.
So, now, if we're trying to find our profit, f of x, we're going to have this revenue, so 15x minus 0.002x squared, if I distribute the x, that's my revenue, minus the cost, so minus a 720 plus 4x plus 0.02x squared. Okay? So simplifying this whole thing here, our profit function is, let's see, the x squared, so we have a negative 0.002 minus 0.02, so that's a minus 0.022x squared. And then we have 15x minus 4x, so that'll be plus 11x, and then a minus 720. Okay? So there's our profit function. And we also want to make sure that we state a domain for this function. Okay? What is the domain going to be for x? Profit, if you're losing money, profit would be negative. But remember, x is the number of items per day. So the number of items per day can't be negative.
And it can't be a fraction.
Very good. It can't be a fraction either. So x, you could just say x is a positive integer.
Okay. Do we always have to do that in those problems? Like, you always have to identify?
You need to identify your domain, definitely. Yeah, because what you could find out is we could do this and we could get a max profit at, say, like
4/3.
Yeah, some fraction thing. Okay, since it has to be an integer, while mathematically the max would occur at 4/3 or whatever, what we would want to do is we would want to check the integers on either side of that. Okay, so we'll look at that here. Now, there's no other thing here that indicates a limitation. Like, they don't tell us what the maximum that is possible for them to make in a day is. Obviously, the minimum would be 0, but we're not going to have any profit if we don't make anything. So we can eliminate that endpoint. All right. So really, the only limitation we need to consider here is it's got to be a positive integer, or a natural number, if you will. So now, we're going to find the first derivative and find the critical values. All right. So what would our f prime of x be in this case?
Negative 0.044 x plus 11.
Good. Okay. And then for our critical values, what do we do?
Make it equal to 0.
Make it equal to 0. Good. So it's equal to 0. So we have a negative 0.044x equals a negative 11. So we divide, and x will be a positive.
250.
Is it 250 exactly?
Yeah.
All right, so they made it work out evenly. All right. If it had been like 250.2, then you would try 250 and 251 to see which one gave you a bigger profit.
Is there like, would it normally be the lower one, or does it not matter?
You would just try it,
Okay.
see which one worked. Okay? Now, one thing you would want to do as well, this is a critical value. We're going to test the endpoints, critical values, and any points where the derivative is not defined. Well, if you look at the derivative, it's a linear, so there are no points where it's not defined. So we don't have to do that. We already mentioned the endpoints. The only endpoint really is 0, because they didn't give us a ceiling for how high it could go. And 0, logically, we're not going to make anything, so we can ignore that.
Wouldn't it be 1?
No, actually, our profit would actually be negative if we tried 0, because if you look, your profit is
Oh yeah.
this minus 720. Those are $720 in fixed costs, whether we produce anything or not. Okay. So really all we have to test is our critical value. Okay. So I'm going to do a sign diagram for 250. And this again is for our f prime. What am I looking for here to prove that that's going to give us a max point?
Yeah.
Yeah, is it increasing here and decreasing here? If you test it out, you plug in, say 100, or let's plug in 1, okay? We plug in 1, we're going to get negative some small fraction plus 11, so that is a positive value, so it is increasing. Then you would want to try something bigger than 250. Let's try 1,000. That'll make it negative 44, plus 11 is a negative 33, so it is decreasing. Okay, so we have this sign diagram that confirms that 250 is the max, okay? 250 yields a max, okay? So, it says find the production level that will maximize profits. So here, what's our final answer? Well, producing 250 items yields a max profit, and just for extra, I might as well say what that profit is. If we plug in the 250 up here, we can figure out what that maximum profit actually is. Okay.
So we plug it in back on the first equation, right?
Yeah, because we're actually trying to figure out what the profit is. So let's see, we have so we have a negative 0.044 times 250 plus 11 times 250 minus 720. And that maximum profit is going to be $2,019. Okay? So that's the best profit we can do every day. We figure that out, stretch it out over the whole year, we can estimate our profits for the whole year. Okay? So, does that make sense?
Yes.
Alright. So, notice the procedure will be basically the same here, regardless of the situation. So, I did want to get one where, here, okay, number 3. Did anyone actually try number 3? Okay, a little bit?
Yeah, I wasn't quite sure where to go with it.
Okay, well let's take a look at this, because this one I want to look at because here we are given a window from 0 to 10,000, so we have endpoints in this example, okay? And we want to construct our cost function. It says how many fittings should be produced daily to minimize total production costs. All right, and it says X is the number of fittings per day. So let's think about this. We have our total costs, and it says we're going to pay 1,000 euros. Is that euros?
Yes.
Okay, euros per day for the workers. It doesn't matter how many fittings we're producing, we're paying that much. So that's just 1,000. Okay? Then it's saying it costs two euros per day per fitting. So that would be
2x.
2x. Okay? And then we need to add to that the cost for running the machines and for maintenance. Okay? And obviously, the more we're producing, the more maintenance we're going to have to perform, the more it's going to cost as far as electricity and all that stuff, running the machine. So this is 5,000 divided by X, okay, per day for running the cost. So we add in the 5,000 divided by X. Okay? So here's our cost function, and notice we want to minimize the production cost. That's why I made the whole thing equal to production costs. All right, remember we're writing the function in terms of what you're trying to minimize or maximize. All right, so what would we do next? Find the derivative, okay? So our derivative would be what?
2
Negative.
minus 5,000 times 2 negative.
X to the negative 2. Good.
Just use negative 5,000 over x squared, right?
Yeah. 2 minus 5,000 over x squared. Okay.
Minus.
It's minus because this was over x, so that's like x to negative 1. So you brought the negative 1 out in front, subtract 1, that's why it's a negative 2. Okay, so now what are we doing? Now that we have the derivative, yeah, critical values, make it equal to 0, okay? So I'm going to add this to both sides, 2 equals 5,000 over x squared. Okay. Do a little more algebra, I get x squared equal to 2,500. Good, x equals 50. Okay? So, x equals 50 fittings. So, here's what we need to do. We found the critical value. Check the sign diagram to see if it's a min, okay? Again, we're using our derivative. So if I plug in, let's see, it can't equal 0, right?
One,
No, just one.
So if we do 1, it's obviously negative. 2 minus 5,000, this is negative. So we're decreasing, that's a good sign. Okay? But then once we get past 500, or 50,
Just put like 100.
yeah, if we put 100 in there, that'll be 10,000. So 2 minus a half is 1.5, so this is positive. Alright, so therefore this is a min point. Okay? This is a min point. Now, we want to test a couple of things here. We haven't had to do this yet. There are 3 possibilities of where our minimum costs are. Okay? One would be at an endpoint of 0. Okay? We know it's undefined there. Alright? So, if we tried 1, okay, let's say our costs, we tried the next closest one to the endpoint that's possible, because this is really the endpoint of the possible results, okay. If we try 1, we get 1,000 plus 2 plus 5,000, so that's $6,002, okay. If we'll produce one item all day. We want to minimize cost, so we also need to check 50. And then we should also check 10,000. Okay? Because that's the other endpoint. That must be, if we ran this factory the whole day non-stop, we could produce 10,000. So we should produce check 10,000. Because you're checking the endpoints. Okay? So, in this case, if we put in 50, what do we get for our total costs?
2,000.
What is it?
2,000.
2,100? Sure it's not 1,200?
Yeah, it's 1,200.
1,200? Okay. So 1,200. And then if we plug in 10,000, well, just looking at the 2x part of it, I know that's going to be 20,000. So I know it's greater than 20,000. I'm not even going to bother figuring out the rest of it. So I now know this is my solution. Okay? So to answer the question, producing 50 fittings yields a min cost of $1,200. Okay? So that's going to minimize our costs. And if we're only producing that many, that means the supply is lower as well, so that we can charge more for them. Means our profits go up a little bit too. Okay? So maybe we don't have competitors who are pumping them out like crazy. Okay? So that's what you would do if you have those kind of endpoints. You won't always necessarily be given endpoints, but you'd have to consider the situation. Are there natural endpoints? Like, for example, let's say we had one like the container before. We have a limit to how tall we want this thing to be, or a limit to how wide, or something like that. Those would create natural boundaries that we would need to test as well. Okay?
Are there always only one limit, one minimum to the functions?
Not necessarily. In this case, it happened to be that way, but we could have ones that kind of go like this.
But then it would be like a Q, like the, okay, I got it.
Yeah, you just have a higher degree in your original equation. But there you would need to figure out, okay, is this higher than this?
And
You
so do we have to take like second derivatives for that or no?
No, it's same thing. If you're
So we
trying to
just take
find,
the first derivative and then we choose which one.
Mhm.
Okay.
Yep.
Because I was confused. I thought we had, when we had more than one, we had to take the second derivative and then get the minimum from that.
no.
When we only need the second derivative, you're trying to find like the rate at which it's changing, or like not the rate at which the like velocity is changing.
So the
Yeah,
so
the
we
rate
want-
at which the change in price is changing,
We
yeah.
have a question like that in this section, or in the
It's not
homework.
really applicable in real life.
Yeah, or not like
It doesn't-
not in this situation, like a factory.
Yeah, I mean, other than motion problems, acceleration, I mean, you could talk about like acceleration of growth, like in a situation where like, you know, maybe a bacteria growth or city growth or something like that. When you're talking about like production costs, it's, the concept is there, but it's not necessarily really that useful.
what does the second derivative really mean?
Well, it's the acceleration, it's the change, it's the rate of change of the rate of change. So our price is changing per fitting, that's our unit price, right? That's our first derivative. If you wanted to look at how that unit price is changing as you produce more units, that would be a second derivative. Again, with this kind of a context, it's not super useful. Others, though, where you have something that's physically growing or shrinking or something, it may be more useful because you can look at the rate of growth of that growth, or you can see if it's speeding up, or if it's
it just-
accelerating,
got it.
or hey, we're still going up, but it's
Or we're
actually
getting it
starting to level off,
lowered.
you know, that sort of thing. Did you?
Yeah, I was
Like
just
that
asking,
question yesterday.
if you find that there's like 2 max points, then
But that's
you would
the
just have to
question
plug it
yesterday.
back into the original equation to see
That was
which
the
one's the
question
actual max
yesterday.
point, right?
Yeah.
Design tech.
And
Yeah,
then
if we
you
got
use that.
2 different critical values, you'd plug them both in, you know, to see
Depending
which
on what
one.
you're looking for, right?
Mhm.
Low profits.
Yeah.
I put,
All right. So
What'd you put?
that's all I'm gonna record.